Well, hello and greetings and welcome to this recording of our webinar, Zone Valves or Circulators, the Ultimate Debate. My name is John Barba and thanks for joining us. This is a re-recording of our live webinar. We had a little bit of a technical difficulty and the recording just stopped at the 45-minute mark. So we're going to re-record this and make it available in its entirety for you to review. So thanks for being with us. With that set aside, let's get right into this debate. Which is better for residential hydronic heating? Is it better to zone with circulators? Is it better to zone with zone valves? Well, that's a pretty good question. All right, that's a really good question, and it's one that we've been arguing about for years. Okay, you've got guys that insist on zoning with circulators, meaning every zone has its very own circulator connected to a relay and to a thermostat. That zone calls, that zone's dedicated circulator turns on and delivers the heat. And they'll insist that that's not only the best way to do it, it's the right way to do it. And then you have a lot of folks that prefer to take the zone valve approach. A lot of times it's fairly regional, but there are intermixed a little bit. But folks will say it's better to have one circulator and multiple zone valves. Thermostat calls for heat, a zone valve opens up. When the end switch on the zone valve is fully open, then the circulator turns on. And they believe that that's not only the best way to do it, but it is, in fact, the right way to do it. And it can get kind of heated. You've got one side that's convinced they're right and they think the other sides are idiots. And then you got the other side that's convinced it's right and they think the other guys are morons. And it can go back and forth. And back in the day, it used to be a fairly heated argument. I remember back in the late 80s when I was a contractor, we had this local wholesale shop that I would go to for my daily supplies. And I had been on vacation for a while, and I came back. It's the first time I'd been in there for maybe a week and a half or so. And as I was driving up, I noticed a handful of vans parked on the far side of the parking lot with a bunch of guys standing outside talking to each other, looking at their watches. And in front of the front door, there was another group of vans and a bunch of guys that were inside getting their supplies for the day. And I'd never seen that kind of a split before. Usually everybody just went in and got their stuff. When I just went in because, I didn't think anything of it. And I got up to the front counter and I asked the counterman, says, what's with everybody waiting outside? I hadn't seen that before. And he goes, oh, you haven't been here for a while. Those are the zone valve guys. We had to make them wait outside. What we got in here are the circulator guys. And I looked at the guy and I go, what the hell are you talking about? And what he said was they had to split them up because there was a brawl there about a week and a half prior, where apparently a guy who was an ardent circulator installer lost a big boiler replacement job to a guy who was an equally ardent zone valve guy. And the guy installing the circulators came in and he was madder than heck, and he was yelling at anybody and everybody with ears that this guy is screwing the industry, he's doing it wrong, and he's making it difficult for people who are doing it right, and only a moron would put in zone valves. And there happened to be a zone valve guy there that said something bright like, oh yeah, and then it turned out they literally had a Pier 6 brawl. So they had to split them up. So Monday, Wednesday, Friday, the circulator guys would go first. The zone valve guys would have to wait until they were done. Tuesday, Thursday, the zone valve guys could go first. The circulator guys would have to wait. And then the following week, they would switch off. And this lasted for kind of a while, right? Made you think, what in the name of Ogie Oglethorpe is going on out here? It eventually the emotions kind of dwindled a little bit, and I think people started to realize that it's not all one or the other. And I believe radiant floor heating had a lot to do with that. How do you zone a radiant floor heating system? Well, you generally do it by putting manifold actuators on a manifold, and manifold actuators on a manifold, it's a zone valve system. Okay, one thermostat might control 3 or 4 loops, but it's a zone valve system if you think about it. So people started to really understand that maybe zone valves weren't the work of Satan. Okay, so that's kind of where we wound up over time. So which is right, which is better? What's the ultimate debate tell us? Are circulators better or are zone valves better? Well, friends, it kind of depends on how you keep score, and I think that's really the best way to look at it. I think in reality, both are good choices. There's nothing wrong with either one. And I will suggest this to you. There's not a person within the sound of my voice that could walk into a house and say with any authority whatsoever, by standing in a hallway saying, yeah, this feels like zone valve heat to me, or this feels like circulator heat to me. You can't really tell from that standpoint now, can you? Now, there are pros and cons to both, but ultimately it is take your pick. Okay, but there are understandably pros and cons to both. Both are good, neither is better, it just depends. And let's talk about some of the differences. Okay, there are some differences when it comes to zoning with circulators versus zoning with zone valves. Why would you zone with circulators? Well, the obvious answer is why not? Okay, why wouldn't you zone with, or circulators, I'm sorry, why wouldn't you zone with circulators? Circulators are pretty doggone reliable, all right? We know those suckers last, and they last a good long time. By the same token, a lot of folks will say, I zone with circulators because of what amounts to redundancy. If I have 5 circulators and 1 circulator goes down, I still have 4 circulators. That's like first grade math, right? That built-in redundancy offers a level of comfort, and I think that's as reasonable and as real of a reason for using circulators as any there is. You have that built-in redundancy. It kind of flies in the face of the first one, though, reliability, but hey, it is what it is. So redundancy, if one circulator goes down, I have other circulators, they're going to have heat. Perfectly legitimate reason for zoning with circulators. The only question I would ask was how many boilers you putting in? Oh, just the one? Okay, well, again, just something to think about. The dirty little secret, I think, when you zone with circulators is this, is if each zone has its own circulator, you really don't have to be all that careful about sizing your circulator if you're worried about undersizing, because the reality is it's virtually impossible in most residential applications to undersize a circulator simply because none of the companies out there that make circulators that would be undersized in most normal residential applications. Now, there may be some radiant floor heating applications where, yeah, you need a little bit more of a higher head circulator. I can certainly understand that. But in most normal hydronic situations, it's virtually impossible to undersize a circulator. That said, that's kind of a double-edged sword, because while it's hard to undersize a circulator, it's wicked easy to oversize a circulator. And oversizing a circulator may actually cause more grief than an undersized circulator will. The only problem you're going to have, and albeit it's a big problem, if you undersize a circulator, you may not be able to deliver the BTUs you need when it's really, really cold out. Okay, that's a big problem. I understand that. But oversizing a circulator surely makes that problem go away, but it creates about 10 or 12 other problems that can seriously impact the overall system-wide efficiency of your hydronic, of the boiler and of the system in general. And it can create service issues further on down the line due to excessive short cycling. We're going to explain that and illustrate it for you so you can kind of see. It's my opinion that we have a tremendously chronic and severe oversizing problem in this industry, and I blame 3-speed circulators for that problem. Everybody loves 3-speed circulators because, hey, it has 3 speeds, right? Low, nobody uses low speed. Medium, people with commitment issues use medium. Everybody goes right to high speed, or what we call contractor no callback mode, because dang it, I know that's going to work. If a little is good, a lot is better. And if a lot is better, everything that son of a gun can give you has got to be the best, right? Well, that, again, has a lot of unintended consequences and can create a lot of problems. We'll illustrate that for you, but first I want to show you basic circulator sizing. For some of you, this may be recap. For some of you, this may be new territory, but you can't just say, this circulator looks good, or I always use this one. It's all about flow, and it's all about head loss. And the math involved with circulator sizing really isn't that difficult. It's addition, subtraction, multiplication, division. Really pretty simple stuff that we learned by the 3rd or 4th grade, all right? But you got to do the math. To really understand circulator sizing, you got to do the math. And to really understand oversizing, you got to understand what the math's telling you. So the first thing we want to do in sizing a circulator is to determine the required gallons per minute flow rate that circulator has to deliver. All right. In hydronics, BTUs are delivered by gallons per minute, the flow rate through the pipe. So what we're going to use to figure out our flow rate is this formula. We call this the universal hydronics formula, and that states that GPM is equal to BTUH divided by the product of delta T times 500. Let's identify those terms. GPM obviously is gallons per minute. That is the flow rate you need to deliver the BTUs required at a given point in time. BTUH, of course, that's the BTU load at a given point in time. The given point in time we're most concerned about is what we call design conditions, or that quote unquote coldest day of the year. We want to design our system to make sure we heat at least then. If we can heat then, we can heat the rest of the winter without any problem. So that's our BTUH load. Typically, we find that through a heat load, a set of heat load calculations. The denominator on that division side is the product of delta T times 500. Delta T is the designed for temperature drop of the fluid as it goes through the heating distribution system, through the zone, if you will. Typically, we design residential hydronics to a delta T of 20 degrees, meaning the water might go out at 180 and come back at 160 for an average water temperature of 170 if you're using a cast iron non-condensing boiler, or in the case of a low temperature modulating condensing boiler, that might be 140 on the supply, 120 return for an average water temperature of 130. Basically what we're saying is the water temperature coming back, we're designing for that water temperature coming back to be 20 degrees less than the water temperature going out. Most residential hydronics will be designed around a 20 degree delta T. 500 is a mathematical constant that we use when we're using 100% water in the system. It comes from multiplying the weight of 1 gallon of water, which weighs 8.33 pounds, times the number of minutes in an hour, that would be 60, times the specific gravity of the fluid, 100% water has a specific gravity of 1, times the specific heat of the fluid, 100% water has a specific heat of 1, because after all, it takes 1 BTU to raise 1 pound of water, 1 degree Fahrenheit in 1 hour, all right? It's a lot of ones. 8.33 times 60 times 1 is 499.8. We'll call it 500, all right? If we start to add glycol to the system, that 500 number is going to get lower, okay? It's going to go down to 490, 470, 460. It depends on the level of concentration we have of glycol. Glycol, first and foremost, weighs more than water. It's a heavier fluid, so that's going to weigh more. It has a different specific gravity and has a different specific heat. It's not as an efficient or effective heat transfer fluid. So that number is going to go down. So the lower the 500 goes, the higher the GPM is going to go. So when you start using a lot of glycol, you may find that you may have to upsize the flow rate in your circulator, which may mean even upsizing a circulator to deliver the BTUs required. That again is just it's a mathematical problem that you'll have to solve. But GPM equals BTUH divided by delta T times 500. Let's find flow, okay? Let's do one. Let's say we have one zone. It's a zone pump system, all right? We're sizing a circulator for this one zone. And from the looks of it, it's a big honking zone, okay? 30,000 BTUs is a big honking zone. So 30,000 BTUs is the load, and I'm designing to a 20 degree delta T, and I'm using 100% water. So based on what we know of the formula, let's fill in the blanks. GPM equals BTUH divided by delta T times 500. So GPM equals 30,000 divided by 20 times 500. If we simplify 20 times 500, that's 10,000. So to figure out our flow rate, we're going to divide 30,000 BTUs by 10,000, all right? And that's going to give us a flow rate of 3 GPM. We're going to need 3 gallons a minute to deliver 30,000 BTUs under design conditions at quote unquote coldest day of the year. As it gets warmer out, that BTU load, of course, is going to go down, right? It's going to go down because it's not as cold out. So the load gets lower. When the load gets lower, the required flow rate is lower. But keep that in mind when we talk about selecting a circulator, because that's kind of an important point. So again, 30,000 BTUs divided by 20 times 500 or 10,000 gives us a required flow rate for this zone of 3 GPM. All right, next up is head loss or friction loss or pressure loss. As that 3 gallons a minute is zipping through the pipe, there's friction loss, right? It's rubbing up against the sides of the pipe. It's hitting fittings and losing pressure there. We have to overcome that pressure differential or that pressure loss. And in our world, we call it head loss. All right, we call it head loss. Now I'm going to show you 2 ways to do this. I'm going to show you the easy way, which is your 4 o'clock Friday afternoon, I got to get this pump sized right and get out of here method, which will always, gentlemen and ladies, be safe. It will always be safe. It will always overstate your head, all right, as long as the pipe size properly, etc. This will overstate your head in some cases by a lot, but it's safe and it's quick and it is easy. Let's take a look at doing it this way. The first thing you need to do is to measure the run. Measure the run of the zone. And by the run, we mean basically the gazouta side of the pump all the way through the system back to the gazinta side of the pump, all right? And that's through anything and everything, but measure that entire run as best you can. If you're replacing a circulator and you can't see all the pipe, you don't really guess. What you do here is you make the best reasonable presumption that you can based on your experience as a pipe fitter and your experience in new construction. You know, if I were running the zone, you know, how long would this pipe be? How long could it possibly be? You want to figure that out as best you can. It's not going to be dead on accurate, but it's better than saying, call it 200 feet. All right. You want to measure the run as best you can. Once you measure the run, we now have to take into account valves and fittings and stuff that's kind of in the way. All right. Fittings and things have pressure drop that's equivalent to lengths of pipe. For example, a 3/4 inch copper elbow has the same pressure drop as 2.5 feet of straight copper pipe. A 45 has the same pressure drop as 1 foot of pipe. A T would have the same pressure drop as about 5 foot of pipe, and so on and so on. Since we can't get up there and measure them all or count them all, we have to kind of estimate and allow for them. So we're going to do that by multiplying our measured run by 1.5. We're going to add 50% to that run to allow for valves and fittings and stuff that's in the way. All right, that's generally a pretty acceptable multiplier to kind of give us what we call the total developed or total equivalent length. If we hammered out all those fittings into straight pieces of pipe, this is how long that run would be. So that's the total developed or total equivalent length. Now to estimate, key word here, the head loss on the high side, we're going to multiply that total developed length by 0.04. And 0.04 represents 4 feet of head loss for every 100 feet of straight, properly sized pipe at the maximum flow rate for that size of pipe. So that's 4 feet of head for every 100 feet of straight, properly sized pipe at the maximum flow rate for that size of pipe. So what we're doing here is we're estimating head as if the flow rate were 4 gallons a minute through 3/4 inch pipe, through 9 gallons a minute through 1 inch pipe, 14 gallons a minute through 1.25 inch pipe, or 22 gallons a minute through 1.5 inch pipe, etc. We're estimating at the highest flow rate for each size of pipe. Now we know our flow rate is going to be 3 gallons a minute, and we're using 3/4 inch pipe as opposed to 4 gallons a minute. So we know we're overestimating our head by a good bit. But this, again, as we said, it's very safe, it's very simple, it's very straightforward. Let's do one, all right? Let's say this total run, to the best of our estimation, is 140 feet. So think about this, gang. This is a big zone, 30,000 BTUs, and it's 140 foot long. That's a good size zone in anybody's book. So 30,000 BTUs, 140 feet long. First thing we want to do is account for the fittings, so we're going to multiply by 1.5. So 140 times 1.5 gives us a total developed or total equivalent length here of 210 feet. 210 feet. If we flattened out all those fittings, we'd have a run of about 210 feet. Now, the last step, to estimate the head loss, I'm going to multiply 210 feet by 0.04. 4 feet of head for every 100 feet of straight, properly sized pipe. And that's going to give me 8.5 feet of head. So my circulator is going to have to be sized to deliver 3 gallons per minute worth of flow while overcoming 8.5 feet of head. Okay, 3 GPM, 8.5 feet of head. That's my so-called service point or duty point. My circulator's got to be able to do at least that. So let's take a look at some circulators now and see what we have here. First look is some single speed 00 series circulators of standard efficiency. All right, and what we have here are a bunch of different circulators ranging from a 003 all the way up to a 008, different pump performance curves as we measure in the factory. Now, down at the bottom of our chart on the x-axis here, we have flow in gallons per minute. And over here on the y-axis, we have total head in feet. Okay, this goes back to charts and graphs and stuff that we did way back in school that we thought was a total waste of our time, right? Today's the day, man, you're going to use this stuff in the real world. So let's take a look at our chart. Down at the bottom, we find 3 gallons per minute. And then over here on the y-axis, we find 8.5 feet ahead. Now all we do is we follow the 2 lines to where they intersect, and there's our requirement right there, 3 gallons a minute at 8.5 feet ahead. Now, if you're looking at selecting a circulator, the first thing that's going to jump out at you is this purple line right here. That's the 006B. By golly, that looks like it's a perfect fit, isn't it? You got 3 gallons a minute, you got 8 feet ahead. What could be better? Well, while that would be a perfect circulator to choose for that application, for that flow and head, understand this about the 006B. The 006B, the B stands for bronze body. All right, it's a domestic hot water recirculation pump with a bronze body and sweat connections and a timer built into it. All right, so what you're going to find is if you were to compare this to say number 5 here, the 007, you might find the 006B is going to be about 2.5 times, maybe even 3 times as expensive as a 007. So while that may be a perfect choice based on the flow and head and the performance curve, from a price and availability standpoint, it's probably not your best choice. All right, you wouldn't use it. You'd be looking at either a 005 or a 007 right here, or a 008. And in reality, what you're going to be choosing would be the 007 in terms of both price availability and the fact that it's actually sized pretty well for this. When sizing a circulator, once you find your service point, you want as little white space as possible between the service point and the line. So the 007 in this case would be a much better choice than, let's say the 008. 008, you see, there's a lot of white space between that point and the line. That white space becomes problematic, as we'll explain. All right. Let me show you some 3-speed circulators and how this starts to come into play. The 0015 standard efficiency 3-speed circulator is it's your standard 3-speed circulator. It has almost the major players out there in the 3-speed circulator world in the residential end are the 0015, the Grundfos 1558, the B&G NRF 22, and there may be a couple of others. And gang, they all have virtually the exact same performance curves. You know, you got low, medium, and high. They're relatively low flow, relatively high head circulators, and they all have virtually the same performance characteristics. This guy, the 0010, is a flatter curve circulator, but this is actually designed to be a replacement circulator for the old B&G 100s, the old Takeo 110s, the old large 3-piece circulators that would go on the return side of these old boilers. So for our purposes, we're going to focus on the 0015 for this exercise. If we were to lay out 3 gallons a minute, 8.5 feet ahead, here's my requirement. And as you will see, boy, that's a little bit above low speed. We'll learn something about this in a few minutes, but just based on what we're looking at, low speed is not something we would choose here. We would probably be looking to medium, or as we said, contractor no callback mode on high. And now's the time we need to become acquainted with something called a system curve. We talked a little bit about system curves in our January session, and I want to talk a little bit more about them as well. A system curve is a unique hydraulic fingerprint, if you will, for a piping circuit. Every piping circuit has its own unique system curve. And a system curve is a mathematical relationship between flow and head. In a particular piping circuit, as flow increases, the head loss or the pressure loss is going to increase exponentially. It's a function of the square of the increase. So it's not really a straight line. The thing shoots up kind of like a rocket ship. There's a math formula for it, and I don't want to bore you to death with the math formula for it, but there is a way of helping to determine your system curve. A system curve, if I were to just draw it out real quick, we have 2 points already. We know 3 at 8.5. We know that's 1 point on our system curve. We also know down here, 0 at 0, right? No flow, no head. Now, if we were to math it out, we might find the system curve might look something like that, all right? What's important about a system curve, and this is critically important, gang, is that the system will operate, always operate where the system curve intersects the pump curve that you're of the circulator that you're using. So if I used the medium speed, even though it says I need 3 at 8.5, I'm not going to get 3 at 8.5. I'm going to get what looks to be about 3 3/4 at about 12.5 feet ahead. I'm going to have more flow than I need. If I choose high speed contractor no callback mode, I'll be up here at about 4 gallons a minute. Okay. Now that may not sound like a problem. That may not sound like a problem. And on one level, gang, it isn't a problem. Can I deliver 30,000 BTUs with 4 gallons a minute? I can do that without breaking a sweat. You throw that thing on high, no one will ever call you and complain that they're cold and tell you that it's your fault. At least not as far as the circulator is concerned. That's why a lot of people, when they put a 3-speed pump in, they ignore the first 2 speeds. Bam, they just go right to contractor no callback mode and get the heck out of there because it works. Sort of. All right, it does deliver the BTUs, and that's step 1. But we have to go back now to the universal hydronics formula. So bear with me a minute. The universal hydronics formula says GPM equals BTUH divided by delta T times 500. All right. So we've done our math already. We know that at a 30,000 BTU load, okay, 30,000 BTUs, I've got at a 20 degree delta T, I need 3 gallons a minute. But I've stuck this thing on high speed, right? I'm not pumping 3 gallons a minute. I'm pumping 4 gallons a minute. Now, some people will say, well, that'll help increase the BTU output. Why? It doesn't need to be more than 30,000 under design conditions. 30,000 is all we need under design conditions. It doesn't matter that we could conceivably get more. It's not much and it doesn't matter. What's going to happen here is 30,000 stays the same. I have a 33% increase in my required flow rate. What that means is I'm going to have about a 25% decrease in my delta T. What does that mean? Well, that means under design conditions, let's say I have a cast iron boiler. I'm gunning for that water to go out at 180 and come back at 160. In this case, it's not doing that. It's going out at 180 and coming back at 165. Okay. I've got a 15 degree temperature rise instead of a 20 degree temperature rise. You tell me what that boiler is going to do. I can hear you saying it right now, even through the recording. That boiler is going to short cycle. It's going to short cycle on the day of the year we want it to short cycle the least. Okay, we want the longest run times under design conditions, right? We're telling it, no, we're over pumping, so you're going to short cycle. Now, a short cycling boiler, friends, as you all know, is not a terribly efficient boiler. It's not as efficient as it could be or as it should be or as advertised. And if we are short cycling, we're also increasing the wear and tear on all of the moving parts from the relay through the circulator, through the burner controls and all that other stuff. All that's getting a little bit more wear and tear than it wants and needs, which leads to premature failure. And gang, this is the best it's ever going to be. All right, this is the best it's ever going to be. What if I'm at 50% load? 50% load is only 15,000 BTUs, but I'm still pumping away at a rate of 4 gallons a minute. My delta T is going to drop to about 7.5, and that short cycling just got kicked into overdrive. All right, and write this down if you can and keep this in your memory bank. Studies will tell us that we will spend a full 50% of the average heating season at 1/3 load or less. All right, 50% of the average heating season is spent at 1/3 load or less. So half of the year, that load on that zone is 10,000 BTUs or less. So at least half of the year, I'm dealing with a delta T that's less than 5. We're short cycling this thing to beat the band, man. All right, you're wondering why things wear out. Now, let's say this was a lower temperature boiler, a modulating condensing boiler, and I want that water going out at 140. I want it coming back at 125. Now we're kind of doubling down on some problems here, because now not only is that boiler going to short cycle, it's going to go out at 140 and come back at 125 instead of 120. So there's a little bit of enhanced short cycling going on. But the other thing is that thing's supposed to condense, right? Condensing boilers will condense a heck of a lot more with the water temperature at 120 than it will at 125. And as it gets warmer out, yeah, we're going to be dealing with outdoor reset, absolutely, but that we're still pumping at a rate of 4 gallons a minute. That delta T is going to get smaller and smaller still. And again, we're going to short cycle and we're going to wear stuff out prematurely. That is the problem right there in a nutshell, gang, of over pumping. All right. And that's why 3-speed pumps are, again, maybe one of the worst things you can use. Yeah, they're convenient. Yeah, we sell them out there every day and we sell a ton of them, but you got to know what you're doing with this thing and you got to know why you're using it. Okay. Not saying that they don't have uses. They absolutely do. But when you just go right to contractor no callback mode without any thought put into it, this is the kind of thing that can come back and haunt your customer. Your customer's never going to be cold, but your customer may find that their system isn't efficient as it could be or should be, and they may find out in 3 to 5 years they've got a pretty big ticket repair bill that they're going to have to pay that's going to wipe out whatever fuel savings they had in the first place. So that's the reality of the situation. How do you come up with a system curve? A lot of people have asked that. How do you come up with a system curve? And in this case, we use, this is from Bell and Gossett, and I love this thing. This is the Bell and Gossett system sizer wheel. All right. And what the Bell and Gossett system sizer wheel does, it does many things. Scale number 5 actually does the math for us to plotting out a system curve. The way you use it is this: the white part in the window, that's your flow rate. And up top here, you can see it says feet ahead. So what I'm doing right here is I'm lining up 3 gallons a minute with 8.5 feet ahead. So that's one of my points. Now I can go in either direction and find other points on the plot. So right here at 2 gallons a minute, you can see the head in that system is a little less than 4 feet. I go all the way down here to 1 gallon a minute, I'm at about 1 foot. All right, 4 gallons a minute, I've jumped up to 15 feet. 5 gallons a minute, I've jumped up to 24 feet. 6 gallons a minute, I'm at 35 feet. So you can see how as flow increases, the head goes up exponentially. So if we were to plot some of these points out on our graph, on our chart here, let's go. I've got 3 at 8.5. All right. I've got 4 at about 16. So I've gone way up. I've gone way up. So again, you can see if I go right to high speed, I'm at almost 4 gallons a minute. I'm at almost 4 gallons a minute. So that's how we come up with the different points on the plot. All right. And then we connect the dots, just like we did in 5th grade math, and we thought this was silly. And then the point we're looking for is the point of intersection between the system curve and the pump curve. The system will always work somewhere on that pump curve. It has to. It can't do anything else because of that pesky thermodynamics thing that says energy in equals energy out. So every time that circulator comes on, it's going to work wherever this system curve intersects the pump curve that we've chosen. Now, lest you think variable speed circulators solve this problem and always gives us the right flow, we got to understand a few things about variable speed circulators. And if you missed the January session, I suggest you go back and watch that one. With a variable speed circulator, they have the potential to vary their speed, but you know what? A delta P type of circulator like the Takeo 0015E3, that's this guy, the 0015E3, it's a 3-setting variable speed delta P circulator. All right. When you use a delta P circulator as a zone pump, it's a fixed speed pump. It's not going to vary its speed. It's going to find its happy spot, but it's not going to vary its speed during its operation. It can't. A delta P pump changes speed to maintain a fixed pressure differential within a piping system, right? But when you use it as a zone pump, there's nothing in that zone that's ever going to tell the pressure differential to change. Ergo, it's not going to vary its speed. It's going to be a fixed speed pump. The thing is, we're going to be smart about it. So let's take a look at this. 3 gallons a minute, 8.5 feet ahead. I'm going to be right about here, right? I'll be right about there. I set this thing to the medium setting. All right. My system curve is going to look kind of like this. All right. Kind of like so. What's going to happen is I want 3 gallons a minute. I might be getting 3.2 GPM. That's not perfect, but it's a damn sight better than the 4 GPM we were doing before. The other thing we're getting is this line out here represents that circulator running at full speed at a full 44 watts. All right. Internally, there are a bunch of different pump performance curves here. This one where we're operating, which might be right here, okay, that particular one might be at, say, 23 watts. All right, so I'm operating at 23 watts instead of 44 watts. But more importantly, when I compare it to a standard efficiency 3-speed pump, I'm working at 23 watts compared to, say, 85 watts. Now we're dealing with some significant electrical savings that basically make the price difference between a regular 3-speed pump and then the 0015E3 go away within a couple of years. They're going to buy this circulator anyway. It's just a matter of whether they get it or not. But the nice thing about this 0015E3 is as we learn more about head, we've got the capabilities of doing some pretty cool things with this, as we will show you. Now, the right way for head loss. We gave you the easy way. Now I want to show you the right way. And what the right way does is it takes flow into account. The easy way just presumes the highest flow rate for each size of pipe. Make it simple, no problems. The right way takes the actual flow rate into account. And you're going to see what kind of a difference that makes. This chart comes to us from the Copper Development Association's Copper Tube Handbook. If you go to the Copper Development Association's website, you can actually download a PDF version of the Copper Tube Handbook. It's maybe the most mind-numbingly boring book I've ever read, but Table 6 is kind of important because Table 6 gives us the pressure loss of water due to friction in types K, L, and M copper, but it gives it to us in PSI per foot of pipe. We deal in feet of head. This is giving it to us in PSI. If we want to convert PSI into feet of head, we do that by multiplying our PSI by 2.31. A column of water 2.31 feet high will have a gauge pressure at the bottom of 1 PSI. That's kind of how that works. So let's take a look at this. Our flow rate was 3 gallons a minute, all right? At 3 gallons a minute in a closed loop hydronic system, we're going to use 3/4 inch type M copper. And if we follow these two to where they intersect, you see the pressure loss due to friction in PSI per foot is 0.009. So it's 0.009 PSI per foot of pipe. Now, overall, we had 140 feet times 1.5 for the fittings. That's 210 feet of pipe times 0.009 PSI per foot. That gives us a total pressure loss through that piping circuit at 3 gallons a minute of 1.9 PSI. 1.9 PSI. To convert that to feet of head, we go ahead and multiply 1.9 times 2.31 feet per PSI. And now we have a real head loss of 4.5 feet. So in reality, we need 3 gallons a minute at 4.5 feet ahead. The easy way overestimated the head. That 1 extra gallon a minute damn near doubled the head loss. So I went from 4.5 up to 8.5. So that's kind of how safe that other formula is. But let's see what this does to our circulator sizing. Now, see where we're at. We're way down here now. Now, all of a sudden, the 003 comes into play. The 005 comes into play. But the 003, again, if you take a look at, at number 3 here, the 006, that's still a stainless steel domestic hot water recirculation pump. The 005 is a cast iron circulator. All right, it is a cast iron circulator, but it's not widely and readily available, and actually is more expensive than the 007. So still the 007 tends to be the default circulator here. And if we were to follow this, out, we'd probably be right around 4 gallons a minute if we extrapolated out the system curve. We'd be right at about 4 gallons a minute, and we'd be where we were before with the 3-speed pump. It's just the way it is. Okay, it's not perfect, but this is the way things have been done for decades until the advent of variable speed pumps. Let's put this sucker together here to get our system curve point. So 3 gallons a minute is 4.5 feet ahead. 2 gallons a minute is about 2 feet ahead. I go to 4 gallons a minute, we're up to 8 feet ahead. 5 gallons a minute looks to be about 12.5. 6 is 18. 7 is 25. All right. So we just, again, as flow goes up, head goes up exponentially. Let's go back and plot this out now, and let's plot this out on a 3-speed circulator. So 3 at 4.5, all right, there's 4 gallons a minute, there's 5 gallons a minute, there's 6 gallons a minute. We connect the dots like so, and you see where we're gonna intersect. So right here, we're up at about contractor no callback mode, now we're up at about 5 gallons a minute. So we're worse off than we were before. All right. With medium speed, where we looked at, we're just under 5 gallons a minute. At low speed, however, low speed's now brought back into play. Low speed's about 3.5 gallons a minute, and that's not bad. But ask yourself this question before looking at this slide: would you have thought that a 30,000 BTU zone that's 140 feet long, would you have thought that you could set that at low speed and have handled it? All right, again, that urge to oversize is powerful. Now you go up to high speed, we've got 66% more flow than we need. If we see double-digit delta T's in this system, I'd be shocked, okay? Maybe on the coldest day of the year, but most of the winter, we're gonna be in single-digit delta T's, and we're gonna short cycle that boiler to an early grave. That's just the way it works, all right? I hope that makes sense to you, because to me, this is advanced hydronics. This is how things actually work in reality, not in theory. If we were to go to the 0015E3 again, now this starts to get really good. We're right here, 3 gallons at 4.5 feet ahead. We set that guy to low speed. We're going to be right here at about 3.1 gallons per minute. And that operating curve, that might be at about 13 watts compared to 44 watts compared to 85 watts if you went to contractor no callback mode. Again, just a much better and more efficient solution. It allows us to get our performance curve that much closer to what we actually need. All righty. Now, we've kind of exhausted circulators. Let's talk about zone valves now. Why zone with zone valves? Well, if you take a look at that picture there, zone valves clearly make you happy, right? That's one happy guy, because he's zoning with zone valves. He's a happy dude. Why zone with zone valves? Well, really, why not? Why not zone with zone valves? Zone valves are pretty doggone reliable in their own right. The wiring and the maintenance is a heck of a lot easier. You got to replace a head. It takes, for those zone sentry zone valves that you're looking at there, it takes all of about 2 seconds to take the head off if you dawdle. And then the wiring is all based on plugs. You unplug them from the old head, plug in the new one, put the new head back on, and you're good to go. So your maintenance and your wiring, low voltage wiring, it's a lot easier, a lot faster, a lot simpler. And we can take up a heck of a lot less space. 1 circulator and 5 zone valves takes up a lot less space than 5 circulators, simply because of the room needed for wiring. So space is important. We no longer get that entire wing of the basement to create our hydronics masterpiece, all right? Now we're more tasked with cramming 10 pounds of hydronic, you know what, into a 5-pound closet, all right? So space is at a premium. Zone valves can help you there. And if you are concerned about overall energy consumption, including electricity, zone valves have to be part of the discussion, all right? 1 circulator and 5 zone valves will use about 80% less electricity than 5 circulators. And the math on that one's really simple, gang. 1 circulator is 80% fewer circulators than 5 circulators, all right? So I've got 1 circulator doing the job where I'm doing rather than 5. And it's the same pump, guys. We'll see that it's going to be the same pump. So understand that. And in reality, let's take a look at something else. Maybe a 3007. Say your kilowatt rate is 15 cents a kilowatt hour, and you're in a normal cold weather part of the US, that maybe that circulator is going to run about 2,500 hours. 3007s for 3 zones, that might cost you about $90 per heating season to run those 3 pumps. 1 007 and 3 zone sentry zone valves, that might cost you about $32. So it's not life-changing money, but there is a difference. All right, there is a difference. So yeah, the redundancy thing, you never can be too sure. I get it. If the pump fails, you got no heat, and that's catastrophic. If I have multiple pumps and one fails, I'm good. But again, we are putting in just the 1 boiler, right? But 2 things to think about there. First off, circulators, as we've said, are pretty doggone reliable, and either way, you're going back for a service call. So to my mind, it really depends on you and the customer, and maybe where the customer is in relation to you. If they're way out in the woods and it's a long drive to do an emergency service call, maybe that redundancy probably has value to both you and them. If they're nearby and they're concerned about electrical consumption and all those other things, and then maybe zone valves might be the marching orders. Okay, it just depends. It depends on what you value, what your customers value. All right. Sizing a circulator for zone valves is very, very simple. All right, it's very simple. First off, we have to size it for the total flow. All right, because we got to presume that under design conditions, all of those zones are going to be open and calling at some given point in time, and the circulator is going to have to feed the beast. It's got to deliver the flow for the entire system. So it's the total flow rate, the load of all of the zones added together in terms of BTUs. Divide that by 10,000. That's the required flow rate for the circulator. All right, so it's total flow, but for head loss, we don't add the head loss of all the circulators together. We simply go for the worst case one, because what we're dealing with here, gang, is a parallel piping system. Okay, this is a parallel piping system, and in a parallel piping system, if my circulator can overcome the head loss of the worst case one, it can certainly overcome the head loss of all of the others. All right, I don't have to add them together because I don't have the same water going through all three. All right, I've got a certain amount of water going through the worst case one. I've got different water going through the others. So I don't have to add them together. I just pick the worst case zone. All right, just pick the worst case zone. And that is why. All right, so let's take a look at this. My total heating load is 75,000 BTUs under design conditions, 75,000 BTUs. 75,000 divided by 20 times 500, our required flow rate would be, say it together out there, friends, 7.5 GPM. So my circulator is going to have to give me 7.5 gallons per minute worth of flow under design conditions. Now for head loss, I simply want to measure the longest run. Again, from the Gazoutta side of the pump all the way back through to the Gazinda side of the pump. How long is that? Now you're looking at a couple things here. Here I'm going through a cast iron boiler. Well, what's the head loss through a cast iron boiler? Hard to tell, but one thing I can say with 100% certainty, the pressure loss through this boiler is a heck of a lot less than the pressure loss through that length of pipe right there. So what we usually tell guys is just consider the boiler as a length of pipe, all right? And use that number, we'll be fine. We'll be fine. Same thing with your air separator. The pressure loss through this air separator, since it's a big open space in the piping, is less than that length of pipe. So just consider it a length of pipe and we're fine. Okay. So we measure that run and then we do our math again. So let's calculate our head. And it's going to be based on the size of the biggest zone. The biggest zone is 3 gallons a minute, 30,000 BTUs, 3 gallons a minute. Our longest zone is 140 feet. It's kind of like that same zone we were just looking at. Total equivalent length is 210. We go back here again, same thing, only different. We're at 4.5 feet ahead. Okay, 210 times 0.009 psi per foot at 3 gallons a minute. It's 1.9 psi times 2.31. That gives us 4.5 feet ahead. So here we have a zone valve system where my circulator needs to deliver 7.5 gallons per minute, but we're at 4.5 feet ahead. All right, 7.5 GPM at 4.5 feet ahead. So we go here, 7.5 GPM, 4.5 feet ahead, 6 GPM and about 3 feet ahead, 5 GPM, I'm looking at about 2, 4, I'm at 1.3, all right, 3 GPM, I'm at 0.7. Let's go the other direction. 6 GPM, or I'm sorry, 8 GPM, I'm at 5, 9 GPM, I'm at 6.5, 10 GPM, I'm at 8, all right, 11 GPM, I'm at almost 10. So again, here is the points on our system curve. Let's go back here and plot those suckers out, all right, and as you can see, my system curve's a little flatter here. I need 7.5 gallons a minute at 4.5 feet ahead. Low speeds right out now. I can't use that. I can, however, use medium or contractor no callback mode. All right. If I go with medium speed, I'm at about 9 3/4 gallons per minute here. So again, my delta T is shrinking, gang, under design conditions. My delta T is going to be shrinking even with all zones open. And if I go all the way to contractor no callback mode, all right, I'm up here at over 11 gallons per minute. My delta T is going to be even smaller, probably a good bit less than 15 degrees virtually all the time. And I'm going to spend a huge chunk of the winter with delta T's of less than 10. It's not quite what we're looking for. All right, but that's kind of what would happen in this example. Now I want to show you something else. If we were to go with the 0015 E3, looky-loo, 7.5 GPM. All right, maybe I'm at 7 5/8 or 7 3/4 gallons per minute under design conditions, but I'm also working on low speed. And as zones close, the pump's going to go slower now. As zones open, the pump's going to go faster as they open and close and change the pressure differential. So now I'm really making this thing sing and dance, and I've got that curve, that performance curve, really, really close to my requirement. Now, I want to show you also what goes on with the smallest zone. There's a separate set of system curves here for the smallest zones, for the smaller zones. My smallest zone is 20,000 BTUs. All right, so 20,000 BTUs is actually 2 gallons per minute. It's 2 gallons per minute, and my total length is 120 feet. So 120 feet times 0.004 psi per foot, that's 0.48 psi times 2.31. Looky-loo, my smallest zone is 2 GPM at 1.1 feet ahead. All right, 2 GPM at 1.1 feet ahead. So I'm right here, and then we just continue to work on up. At 3 gallons per minute, I'm at about 2.5. 4 gallons per minute, I'm a little less than 4.5. 5 gallons per minute, I'm at almost 7. 6 gallons per minute, I'm at almost 10. Okay, so there's the system curve plot for the smallest zone. So let's put those out on here. Okay, and here we have the operation here. You know, I was kind of out here with all zones calling. With my one smallest zone, if I'm at medium speed, I need to look at what I'm giving it. I'm giving it 6. That's 3 times as much flow. I'm never going to see double digits. I'm never going to break double digits in terms of delta T there. Never going to happen. And if I'm at high speed, I'm at 7 gallons a minute, and that just gets crazy. But here's the other thing. My delta T, I'm going to have delta T nightmares all year long with this thing, number one. But number two, as these zones close, look what kind of head pressure differential I'm closing against. 13 feet ahead here instead of down here, instead of where I really need to be, which is down here at 4.5 feet. What's going to happen here, friends, is when those zone valves close, it is very, very likely as we move up this pump curve, it's very, very likely that we're going to experience banging zone valves. You're going to hear like a water hammer when that zone valve closes. And that's not a problem with the circulator. It's not a problem with the zone valve. It's a problem with the marriage between the zone valve and the circulator. It's the wrong pump for this application. When zone valves close against pressure differentials up here, they tend to make noise. They let you know they're not happy by banging. So you got to deal with banging zone valves. How do you deal with banging zone valves? Well, there's two things. One way is to put in what they call a pressure differential bypass valve, which does exactly what the name says. It lets that pressure differential bypass the system so we don't bang on zone valves. But in reality, what a pressure differential bypass valve does is it turns a steep curve pump into a flat curve pump. All right. If that's the case, why not put a flat curve pump in the first place? It seems kind of dumb to me to put in a pump that's going to cause a problem, and then 3 feet later spend some more of your customers' money to solve the problem that you just created. To me, that doesn't make any sense whatsoever. Some people can make it sound pretty, but it is what it is. It doesn't make any sense. Use a flat curve pump with zone valves and you eliminate the problem in the first place. Now, variable speed circulators take care of that as well. We're working on this pump performance curve. We've basically eliminated this part of the circulator. So again, if we go with the system curve, that doesn't look so good. I need 2. I'm getting 4.5. My delta T is still going to be kind of on the narrow side here, not like it could be. With all zones calling, I'm way out here, so I'm bopping back and forth between these 2 points, which is very, very good. This is a better solution than I had otherwise, but understand it's not a perfect solution. And gang, there's no magic button that you can push to have this circulator figure out that all zones calling it should be up here, but one zone calling I suddenly have to go completely against how I'm made and work down here. It doesn't work that way. There's no auto adapt or active adapt button that's going to make that happen. Okay, it just doesn't work that way. What you can do is use a delta T circulator. This is the Takeo VT2218. All right, and what the 2218 is, it is a delta T circulator. It's a delta T circulator that will vary its speed to maintain a fixed delta T within the system. We designed it to a 20. What's the great crime in giving it a 20? No one's ever been able to adequately explain that one to me, but that's what people claim. There's no great crime here. 7.5 gallons a minute, 4.5 feet ahead. Here's my performance curve. That's the fastest that pump is ever going to run. My maximum speed right here at line B, that's 59 watts, and my minimum speed right here is 9 watts. So this looks like it's about halfway. That might be a maximum speed of about 30 watts. That's with all zones calling. With one zone calling, I'm I'm way down here, 2 gallons a minute, 1.1 feet ahead. Well, this is the minimum speed. I can't work there. I got to work there. So am I going to have a 20-degree delta T with that one zone calling? No, I am not. Might be about 15, 16, 17 in there, but the point is it's not going to be 8. Okay, that's the point. Now, what's going to happen as zones open? Pump's going to go faster till I get to that point. As zones close, pump's going to go slower until I hit the minimum speed. So I'm working between 9 and 30 watts, okay, under design conditions. Here's the other thing. As it gets warmer out, the BTU load goes down. So remember, GPM equals BTUH divided by delta T times 500. If the delta T is fixed and the load goes down because it gets warmer out, well, the flow has to go down too. That's just the way it is. I'm not taking as much energy out of the fluid. The sensor on the return side of this circulator is going to sense that the water temperature coming back is getting warmer. The delta T is getting smaller. The pump's going to slow down. It's pretty simple. So what's going to happen over the course of the winter is this line here and all of the lines associated with it are going to drop as well as it gets warmer out to a point. At some point over the winter, this is going to be a fixed speed 9-watt pump, basically delivering all the BTUs you need for this structure under design conditions and as it gets warmer. So as it gets warmer, pump's certainly not going to run as fast. You will reach a point where it's no longer a variable speed pump. You will reach a point where it's a fixed speed 9-watt pump, and you'll reach a point where you don't have a 20-degree delta T. It's going to be lower. It's going to be operating like a fixed speed pump. The point is it's not going to be operating at 85 watts, and you're not going to have single-digit delta Ts. That's the benefit of a delta T pump. Lastly, let's look at a bigger job. Let's say this is 120,000 BTUs, and I've got 3 zones, and each zone is exactly the same load, exactly the same size. It's theoretical, but we want to make a point here. 12 gallons per minute, 120,000 BTUs is 12 gallons a minute. Each zone is 40,000 BTUs, that's 4 gallons a minute, and the total length for each zone is 200 feet. So the flow and head are going to be the same for each zone. All right. If we were to math that out, we're going to find that we're talking about 7 feet ahead per zone. 12 gallons a minute is the total flow. 7 feet ahead is what I have to overcome. So I need 12 gallons per minute at 7 feet ahead. Let's take a look at what we have here. 12 gallons a minute, 7 feet ahead. All right. Low and medium are off the table, right? I have to go to high here. I have to go to high, and I'm going to be operating out here maybe at about 12 and a half, 13 gallons a minute. Reality, that's not bad as far as circulator sizing goes, as far as delta T goes. That's not going to be horrible. All right. But let's take a look at our smallest zone, 4 gallons a minute, 7 feet ahead. In reality, if I take a look at my system sizer wheel, I'll find it. Okay, at 6 gallons a minute, I'm up here at about 15 feet ahead. I'm going to be operating right around here with one zone calling, my smallest zone calling at about 14 feet ahead. And you can tell right now that we're probably going to have banging zone valve issues. We won't have banging zone valve issues here where all zones are calling and then one closes. We're going to have banging zone valve issues up towards there. So they're not going to bang all the time. It's going to bang some of the time. All right. That's just the reality of using this particular circulator. Can we use the 0015E3? No, we cannot. All right, 12 gallons a minute, 7 feet ahead. That's outside of our maximum speed. That's not a good, this circulator is not a good choice for that application. But we can look at the VT2218. This is where a delta T pump really starts to sparkle and shine. I'm at 12 gallons a minute, 7 feet ahead. I'm almost at full speed out here. With all zones calling, I'm almost at full speed. With one zone, my one smallest zone calling, 4 gallons a minute at 7 feet ahead, I'm here. So under design conditions, I have a pretty wide range of variability in my speed. On top of that, I still have a long way to go as it warms up. So the warmer it gets, I have a lot more variable speed, a wider wedge of variable speededness, if you will, over the course of that heating season. Now, again, at some point when it's milder, I'm going to be working down here at minimum speed at 9 watts. But in this case, we're going to have as wide of a delta T as we can possibly have for as much of the heating season as we can possibly have. For that application, in this case, the VT2218 makes a ton of sense. Smaller systems, the value can be debated, but in this type of an application, this thing really does sparkle and shine, as we said. Alrighty, I hope that shed a little bit of light on the difference between circulators and zone valves. Again, no real difference in terms of delivering the BTUs. It's simply a different route to the same destination. Doesn't matter which way you go. Understand that over pumping is going to severely limit the overall efficiency of the system. No one may freeze to death on your watch, and that truly is important. But the more you know about circulator sizing, all right, and the more you understand about the dangers of overpumping, the more you can understand how systems and how parts and pieces and components and boilers and whatnot could wear out prematurely, creating a rather uncomfortable discussion on why after 4.5 years you got to replace a combustion, an igniter or an ignition module or something that's a fairly big ticket item. Okay, that's never a comfortable conversation, and you'll understand why the efficiency may not be as good as it could be or should be. Yeah, your combustion analysis tests are going to really look good, but the system itself isn't as efficient as it could be or as it should be, and again, it's because of the overpumping with the circulator. Variable speed circulators give us the ability to fine-tune systems about as well as they can be fine-tuned today, whether it's a delta P pump or a delta T pump. But you know what you're holding in your hand and you know what it's doing. Most importantly, you got to know what it's not doing. Again, there's no such thing as magic here. There's no such thing as a circulator that does the thinking for you, and there's no such thing as a circulator that takes the thinking out of it. Machines haven't taken over yet, gang. All of these things require your professionalism, your knowledge, and your know-how to set them up to operate overall as a unit at its peak efficiency. And that's what professionals do, and that's why we have these webinars for you, for you professionals. So with that, thank you very much, guys, for joining us and gals as well. If you do have any questions, please feel free. My email address is johbar@takocomfort.com. It's more fun doing it that way than having it typed out. So johbar@takocomfort.com. Please send me an email anytime you want. I'll do my very best to answer it in a timely fashion for you. So thanks again, and we will see you next month on Taco Tuesday. So long.